I think we'll take more questions offline. And then our next talk is by Moshe Babaioff. Pizzas, lemons, and cookies. Is that a promise?
Yeah. Yeah, I'll try to fulfill the cookies will be downstairs later. Okay, so this is a joint work with, do you hear me? Yeah, okay. So it's a joint work with Itai Avraham from Microsoft Research Silicon Valley and Susan Etty, which is in Harvard and the chief scientist of Microsoft, and Michael Grubb from MIT. And okay, so. Okay, so I guess I won't talk about Angry Birds. I actually will talk about selling display ads. So we want to design a good auction to sell display ads, and actually I'll be interested in two things. First, understanding what happens in market for display ads, and second, try to think about how we should optimally design those markets. And traditionally, these display ads were sold by negotiation. So, you know, a guy from MSN would meet some representative of Nissan. They would sit together, maybe play golf, and sell 10,000 impressions or 1 million impressions for the next month for some price. And now there is a shift from these big deals in which they sell lots of impressions together to real-time markets in which they will sell one display ad at a time. So actually, when the user will request for this MSN page, then they will run an auction between different advertisers in order to decide which ad will be displayed at this slot, and then decide who is going to get this ad slot and present this ad. So this is a little bit like sponsor search, in which when somebody searches, then there is an auction to decide which ads will be shown. But there are interesting characteristics that are different from sponsor search, and I'll try to talk about them. So let's think about this real-time market for display ads, and I'll present a very stylized model in which we have this seller. AdECN is the Microsoft platform, but there are platforms for Yahoo and Google. And there is the publisher. Publisher is, in this case, the guy that has the web page. And there are these advertisers that are interested in these impressions. And once an impression comes, the publisher is going to send it to the market, to the seller, in order to sell it to the advertisers. Some of these advertisers are actually going to bid in advance. So they are not participating in this real-time market. They don't have the technology, or different reasons they might actually decide to bid in advance. But some of them actually are going to bid in real time. So the publisher, when he gets this request for a web page, will send this request to the auctioneer. The auctioneer will send the information to the advertisers. And these advertisers have cookies on the user's machine, so they can try to figure out what's the value for that impression, given the information that they have about the page, given the context of the user. And from that, they will decide how much to bid. So you can think, for example, about Amazon. They might have a cookie on your machine. They know how much you buy online, and then they decide, you know, since you are buying a lot of online, they will be willing to pay a lot for displaying some advertising to you. And then the auctioneer would run an auction. We will focus, in the first part of the talk, I'll focus about second price auction with random tie-breaking rule. Decide who is going to win the item. And this guy is going to be allocated the impression, which basically means that he will need to provide the ad that will be displayed to the user. So that's a very stylized model of these real-time markets. Okay, so what are the characteristics of these markets? We have real-time allocation. Every time an impression comes, we need to decide who is going to be displayed. And a very important feature is asymmetry of information. So different advertisers have different information that they can get about this user given their cookies on the machine. So, you know, Amazon has some information about you. eBay might have some different information about you. And that would be very crucial. And here are the three examples for this kind of markets. AdECN is the Microsoft market. DoubleClick is Google's. And Right Media is Yahoo's. Okay, so how should we model the valuation of the users in such a setting? So it seems reasonable to actually believe that this is a correlated value setting. So what I mean by correlated value, everybody might agree that an impression by a human is better than an impression by a bot. But a human that is searching for a car might be of more interest to car dealers than a human that is currently interested in buying a watch. So there is some correlation in the valuation between the different impressions, they do agree at some extent on the valuation, but there is some difference between the different advertisers. But at least at first approximation, we'll think about this as a common value auction. So in this common value auction, all the advertisers actually agree that let's say a human with a high income is better than a bot, and will be interested rather by impression from a human. And this creates this kind of information asymmetry in a common value auction. Okay, so let's start with a very simple example in which we have this kind of common value auction, and we have only two types. Either it's a good impression, it's a pitch, or it's a lemon. And we don't observe the value. And we have a common prior. We assume that both are equally likely, so we can compute the unconditional expectation given that's the expected value of this impression. And we think about, first think about two bidders. One is informed at some extent. He has a cookie on the user machine, and he can update his belief about the common value. And the other is completely uninformed, so he's maybe doesn't have cookies at all, or he's bidding in advance before the impression is realized. Okay, so what will happen in this second price auction when we have a common value and asymmetry of information? So we have this one, a bidder one is perfectly informed, bidder two is completely uninformed. How should bidder one bid? He knows exactly what's the value of the impression. He will bid his value. So that's easy. The hard part is figuring out how much the uninformed is going to bid. And what I claim here is that for every X that he bid, that's a Nash equilibrium. Why is that? Because essentially, every bid that he submits, he either loses and gets 0, or he wins and he pays exactly the value because the informed guy is bidding the value, right? The informed guy actually knows the value, so he bids the value. And since he's paying the second highest bid, he's bidding exactly the right amount. So for any X, his utility is 0, and we have this multiplicity of equilibria. And we don't know how much revenue will be extracted, right? For every X, you'll get different revenue. If X is H, then our revenue will be optimal. It will be equal to the unconditional expectation. If X is L, then our revenue is going to be L because the second bid is always L. So that's actually quite problematic. So what should we do about that? So since we have multiplicity of equilibria, we suggest a refinement to choose between all these different equilibria. And our refinement is supposed to capture this intuition that in the games that we've seen before, the uninformed is so disadvantaged that he shouldn't be aggressive. So he takes a risk by bidding higher than 0 or higher than L, but gain nothing out of that. And the way that we want to model the fact that this is a risk is by saying that there is some tiny probability that another bidder will arrive to the auction and submit, let's say, submit a uniform random bid between 0 and 1, between L and H. So we call this new game an epsilon R Tremble of the game, in which this additional bidder is entering with probability epsilon and is bidding with distribution R, and think about R as the uniform distribution between L and H. And the equilibrium notion, which we call Tremble robust equilibrium, is, loosely speaking, we look at the limit of this sequence of Nash equilibrium when we take epsilon to 0. And the limit of that would be our Tremble robust equilibrium. So let's go back. Maybe before we go back to the example, I'll just point out that we need this new solution concept because the other ones that we've tried, like iterative elimination of dominated strategies or perfect hand, Tremble hand perfect equilibrium, don't work. They don't give us these unique solutions that we want in this simple setting. So with this Tremble, we recall that we have this multiplicity of equilibria. What happens now when we have this Tremble? So there is a positive probability that the random bidder is bidding anywhere between L and H. So any aggressive bid by the uninformed will result with a positive expected payment. But he is going to get an item of value L and going to pay more than L in expectation. So any bid over L is actually dominated now. So he cannot bid more than L. And therefore, the only equilibrium that survive, the unique equilibrium now is going to be for the uninformed to bid L, and the revenue is going to be L. So we think of that equilibrium as the most reasonable equilibrium when we have a guy that's informed and a guy that is uninformed. OK, so that now I
Isn't it a strict equilibrium? Did you examine the relation of strict equilibrium?
strict. What's the mean? I'm not familiar
Well, I
with.
guess you could phrase this thing in some sort of evolutionary model in which players have mutations.
Okay.
Do you know the concept of evolutionary stable strategy?
Yeah. Yes.
Is it connected any way to this concept?
We didn't spend any time thinking about that, but I'll be happy to discuss that with you later. OK, so we promised you peaches and lemons, so let's now talk about peaches and lemons. So think about a model in which we have this one uninformed guy and one informed guy, and he has three possible signals. One is that if the value is high, if it's a pitch, then he gets the high signal with probability epsilon h. The other one is that if the value is actually low, he gets the low signal with probability epsilon L, and otherwise he gets the default signal. So we'll now play with the different parameters from this epsilon L and epsilon H and see what happens. So the first scenario is what's called cream skimming. What's cream skimming? Cream skimming is this informed guy has positive probability of knowing about pitches when there are actually pitches, and zero probability of knowing about lemons. So in that case, when he sees a pitch, he should definitely bid high, right? He knows for sure that that's a pitch. So he bids high. When he doesn't see a pitch, he sees a default signal, then he should compute what is my expected value given the fact that I didn't see a pitch. So he will update his posterior belief about the value of the impression. Oops, sorry. And he will figure out that actually it's a little bit less than the unconditional expectation, and he'll bid that. And the uninformed, as we've seen before, because of this Tremble, should be the E minus. And the revenue is going to be E minus. Now, what's interesting is then now think about this case which we call the avoiding lemons. The avoiding lemons case is the case in which he doesn't know about pitches. He only knows about lemons with some tiny probability. So he has some technology to figure out if an impression is a bot. And with some tiny probability, he actually knows that an impression comes from a bot. So when he sees a low value impression, he will bid low. When he doesn't see the low value impression, he sees a default signal, he will bid a little bit more than the unconditional expectation because he's updating his belief. And the uninformed guy, as we've seen before, should bid L. So we see that with tiny probability of the informed guy knowing about a low value impression, the revenue is going to actually collapse to L. So there is a huge implication on the revenue of the auctioneer from this asymmetry of information. And finally, in the general case, when both are positive, then he has three possible bids. If he sees low, he bids low. If he sees high, he bids high. And if he sees the default signal, then he just computes his posterior. But still, the uninformed is going to bid low, and the revenue is going to be equal to the expected value given the lowest signal. OK, so I guess the name lemons, I guess many people would figure out by now that it seems somewhat related to Akerlof markets for lemons. So the Akerlof markets for lemons is this market in which sellers are selling used cars, and they know the quality of the car, but the buyers don't. And then because of that asymmetry, only bad cars will be sold in this market. And I want to point out two differences between these markets and our markets. So actually, in our markets, uninformed bidder can actually win high-value items in a Nash equilibrium, and there is multiplicity of equilibria. So actually, in some sense, our Tremble robust refinement, the role of this refinement is to retrieve this intuitive outcome in which when there is this asymmetry of information, then there should be a collapse as a unique prediction. Okay, so let me briefly talk about the outline of the rest of the talk. I'll just formally define our model. I'll talk about the single informed bidder, which basically we've seen. And then the heart of this paper is actually trying to understand what happens if we have two bidders and both of them gets information about the value. And then finally, I'll talk about the mechanism design issue. Okay, so what's the model? So it's a Bayesian model. We have a state of the world omega that's unobservable. We have sets of signals for each agent, and each agent gets a private signal about the state. We have common prior, and the common value is dependent on the state, which is not observable. And now we define this Tremble. This Tremble of the game is actually the same game in which we have this random bidder that appears with probability epsilon and is bidding according to this distribution R. And you can think about R as a uniform distribution. It's a nice distribution that has full support and differential and everything. And our definition of this Tremble robust equilibrium is the following. We want mu to be a Tremble robust equilibrium, so it should be a Nash equilibrium, so it's actually a refinement. And we look at any sequence of epsilons that goes to 0 and look at the Nash equilibrium in these trembles of the game. And what we want is that for every agent and every signal that he receives, he might play a distribution, right? It might be a mixed strategy. We want the mixed strategies that he plays to converge to the mixed strategies that he should play according to mu. And we also define this stronger notion of strong Tremble robust equilibrium in which basically you can think of it as this equilibrium does not depend on epsilon. At some point they play strategies that don't depend on epsilon, and that was exactly the case when we have only one informed bidder. They were bidding independent of epsilon. Okay, so in a single informed bidder, we basically seen that. If there is only one informed, he will bid his posterior, and each of the uninformed bidders will bid according to the lowest signal, and then we have a unique Tremble robust equilibrium with everybody bidding according to these strategies. And it's actually strong equilibrium. It's independent of epsilon. And the implication, we've seen that. Basically, revenue will collapse to the value condition on the lowest signal. And that's independent of the probability of this lowest signal being realized. So that's quite simple. But of course, the interesting question is what happens in a more complex information structure in which more than one agent is informed. So let's move to the two bidders binary signal case. So how should we think about this case? So think about two bidders. Each of them has a technology to figure out whether an impression is a bot or a human, but they have mistakes. So given the information that this signal, they can update their posterior about the value of the impression. And of course, if both algorithms agree that it's not a bot, it's better information than only one of them. So we have these two signals, the low signal and the high signal, and both of them have positive probability, and we also assume that both of them can get the high signal for the problem to be interesting. And we can normalize the value conditional on both of them getting the low signal to 0 and the high signal to 1. And then the value if agent 1 gets the high signal and agent 2 gets the low signal is V1, and here we have V2. And we basically consider monotonic domains in which more good news is better, so more high signals is better. So it means that if you only get one high signal, then the value is less than 1 and between 0 and 1. Okay, a special case of this is the symmetric case. In the symmetric case, both of them have the same value and the same probabilities. And that case was actually solved by Milgrom-Weber in this classical paper from '82. And basically, in this paper, they observed that this symmetric equilibrium in which, when you get the high signal, you bid according to the value of 1. That's an equilibrium. So first, let me discuss two special cases. So the first special case is when both agents actually, when they see the high signal, they know for sure that the value is 1. So that's a very easy case If they know for sure that the value is 1, then they know what to do. If they see a high value, they will bid 1. If they see the low values, they will bid 0. And that's the unique equilibrium in a unique Tremble robust equilibrium. So think about these 3 examples. In this example, there is zero probability of getting this high-low combination. In this example, the value is 1, even if only one of them gets the high signal. And we can see in general that in order to satisfy this condition, these products of the probability times 1 minus the value must be 0 for both agents. So that's the conditions that ensures that both of them are informed. The other case is the case in which agent 1 is perfectly informed about high. So he knows that if he gets the high signal, the value is 1. And agent 2 has lower value. In this case, agent 1 should be more aggressive because he knows the value, but the other agent doesn't. So he's going to bid 1 when he sees the high signal, and the agent 2 is going to bid the lowest possible value conditional on that information, which is V2. And this is again the unique one. Now, the general case is the case in which both of them are positive, and let's assume without loss of generality that agent 1 has the higher product of the higher of these 2. And note that in particular, it means that if I see a high signal, I don't know for sure what the value is, right? I don't know for sure that the value is 1. My expected value given the high signal is less than 1. So that's the general case. For this general case, even for the special case in which the values, the V1 and V2 are 0, it's like a riddle to understand what should be the equilibrium. So there are multiplicity of equilibrium, but it seems like one should be chosen, and we don't really know which one should be chosen, so that we had to dig in and actually find out the solution without actually planning for that. So one possibility is for agent 1 to bid 1 when he sees the high signal, and agent 2 bid 0 when he sees the high signal. So that's definitely an equilibrium because agent 1 is happy, and agent 2 cannot win the good items unless he bids more than 1, and then he pays 1. And this is also an equilibrium for agent 2 to bid 1, and both of them having utility 0. So which equilibrium should be chosen? Maybe a mixed equilibrium. And if a mixed equilibrium, which mixed equilibrium? So here's our result. So the result is the following. Assume that we have this inequality without loss of generality. In the unique equilibrium, bidder 1, both bidders will bid 0 when they see the low signal. Bidder 1, which is the stronger bidder, is going to bid 1 when he sees the high signal. And bidder 2 actually is going to be the mixed strategy. He's going to bid 1 with this probability that is exactly the ratio between these two numbers. And he's going to bid low, V2, with the remaining probability. So okay. So given this result, we can interpret this product of the probability of HILJ times 1 minus VI as the strength of the bidder. The bidder that has lower product is the stronger bidder, and he's going to bid more aggressively. And the stronger bidder, the strength is actually equals to the loss that bidder I with signal HI is taking by bidding 1. If he has random, if the random bidder is going to bid 1. So in a sense, the guy that have a larger possible loss is the guy that is going to bid less aggressively. So here's the special case. When two agents are symmetric, we know that the Nash equilibrium that Milgram-Weber gives is the equilibrium in which agent with high signal is bidding 1. That's exactly the ones that we are going to predict with our Tremble robust equilibrium refinement. And basically, we show that this is unique. And we also, our refinement enables us to get unique predictions in the asymmetric cases. So in the symmetric case, it's really easy to justify the symmetric equilibrium. In asymmetric cases, it's not so easy to figure out which one should be chosen. And also know that the revenue prediction, we have some kind of revenue prediction. If the values are 0, then the revenue prediction is exactly proportional to the ratio between the two probabilities. So in a sense, this ratio reflects the exclusive Lemon information ratio. The probability of H1 L2 is exactly the case in which L2 has exclusive information that that's actually a lemon. Oh, so let me briefly talk about the idea of the proof. What we do is basically present the necessary conditions for an equilibrium in this tremble of the game, and then show that an equilibrium exists. That's actually a non-trivial statement because we have infinite bit spaces and non-continuous utility spaces. And then we show that the limit of any sequence of equilibrium must be exactly what we predicted. So the first step would be to understand how agents will bid. So these two lines represent the support of the bids. And here we basically see that in the case that in one case in which the values must be equal, both of them are going to bid with full support between some value B min and some other value B max. And there are no atoms and no flat places in this interval between B min and B max. So that would be the first stage. Another possible case is that there is an atom for agent J, and both of them are bidding continuously on this interval. And the third option is for agent J to have an atom, and then for agent I to have an atom at B min, and both of them bidding on this interval. And then in this third case, we can compute actually what's the value of B min, and we can also compute what's the size of this atom, since agent J must be indifferent between bidding his atom and bidding in his support. So this gives us some handle on the size of this atom. And the important thing about this thing is that it goes to 0 when epsilon goes to 0. So the exact formula doesn't matter so much, but what you see in all these three options that are possible, agent I's atom goes to 0 as epsilon goes to 0. And that's, if you recall the Tremble robust equilibriums that we predict, agent 1 is actually going to bid H1 with probability 1. So he has no atom below 1. OK. This first case can only happen with if and only if agents are symmetric. So that's not very interesting. And then given the fact that an agent must be indifferent between all his bids in the support, we can actually compute what would be the CDF for the bids of agent I. And we have this formula, and this exact formula, again, it's not very important. But we can use this formula in order to figure out what would be the size of the atom for agent 2 at V2. So let's see how we do that. We look at the agent, at both agents, they have this formula for their CDF. And we know that at B max, both of them are bidding, the cumulative distribution is 1. So we can replace B by B max and move this thing to the left-hand side. And then we can divide the two for the two agents and get this ratio. Once we have this ratio, you can see that this ratio is very, very similar to the strength ratio. We have this function B that goes to 1 when epsilon goes to 0. And we have this function T that goes to 1 when epsilon goes to 0. So basically, we can figure out the size of the atom for agent 2. And this atom size is exactly 1 minus the strength ratio. And this basically gives us the result. And the fact that this fraction is smaller than 1 by our assumption that agent 1 has the smaller product gives us that agent 1 actually have this small atom that goes to 0, and agent 2 is the guy with the high atom at V2. That's actually the way that you differentiate between the two agents. And here you can see an example for these CDFs of the two agents. So this is the CDF for agent 1. This is the CDF for agent 2 for some parameters. And you see that agent 2 is bidding an atom at V2. And then he has this continuous bidding between B min and B max, which is very close to 1. So we can't see that. And this is actually even for epsilon that is quite large. And agent 1 is going to bid continuously. And there is some ratio that is reflected by these formulas between the CDFs of the two. And when epsilon goes to 0, basically agent 2 is going to bid this atom, and then very flat, and then he's going to bid very dense around 1, and agent 1 is going to bid very densely around 1. This is becoming flat and flat. And in the limit, we have exactly what we want. Okay, how much time do I have?
Just 3 minutes.
3 minutes. Okay, so let me briefly talk about the mechanism design. So up to this point, I was thinking about the second price auction as a fixed auction and try to figure out what's happening in this auction. But now you can ask, how should we design, as mechanism designer, how should we design an auction when we have this asymmetry of information? So if we want to maximize revenue, note that in a common value auction, every allocation is efficient, right? It doesn't really matter who gets the item. So the goal might be maximizing revenue. And we saw that second price auction, when we have only one informed, has very low revenue. But it's actually quite trivial to get excellent revenue. Let's just block these cookies. Don't let anyone see any information. Or alternatively, always allocate it to the uninformed bidder and just ask him to pay the expectation. And then we have perfect revenue. But clearly, this misses the entire point of these exchanges. So the entire point of these exchanges is to enable the advertisers to use the cookies that they have on the user's machine to show specific ads, to do what's called ad targeting, to show specific ads to this specific user in order to boost the value over just the common value. So the way that we think about that is this kind of bidders being able to tailor the ad specifically to the user, and they get another extra bonus over the common value. So there is this common value, and actually this is kind of a correlated value setting. There is a common value and this extra bonus that a guy that have a cookie can get by presenting the right ad. And it turned out that our revenue collapse results also hold when you have one informed bidder that is able to get this extra boost. So let's think about this model in which we have a random advertiser that is informed. If now we decide on the allocation in advance, we'll get a very bad result because we are only going to get this bonus with probability, let's say if we do it at random, with probability 1 over n, right? Because a random advertiser is informed. So we actually must allocate in real time in order to maximize the social welfare and the possibility of getting the entire revenue. And we can do this with the second price auction, but our result says that revenue will be quite poor in this case. So it doesn't give us a good solution revenue perspective. But we can actually get full revenue extraction if we charge entry fees. So if we have full knowledge about the environment, we know exactly the priors and everything. We can compute what would be the expected utility of every buyer from participating in this auction, and just charge this in advance as an entry fee. And this kind of mechanisms might not be reasonable because we have an ex ante individually it's only ex ante individually rational, which means that I might charge somebody the expectation, but only he, at the end of the day, only gets a low value item, right? So that might be not very reasonable, but maybe in this setting, since we have actually millions of impressions and each one is actually a very tiny deal, then on average, everything will be fine. So it's not. What do you mean fixed price?
Just set a price to the impression. I mean, if you have full information.
No. So the allocation must be in real time because only the guy that has the cookie is able to serve the specific ad to get the bonus, right? So I need to allocate to him.
Price it at slightly less than the bonus.
So that one. So you say I'll charge the. Who is going to get the item? Ex ante before everybody is willing to bid exactly the same. I need to decide who is going to get the item, right? I must do it in real time. If you do it in advance, then you can't do better than just choosing at random, choosing one guy at random, right? How will you break ties, right? Yes, 1 minute over. Okay, so. Okay, I'll just say that we have solutions that are very similar to Marathon. Marathon private value optimal auctions give us inspiration to get a mechanism that is almost optimal. It gets 1 minus 1 over n fraction with the welfare. And we can do that even if we don't know the conditional expectation by losing a little bit more. Okay, so let me summarize. We think about this asymmetric information in common value auction. We came up with some new refinement of Nash equilibrium that enable us to give a unique prediction in many interesting cases, and we see that there is a revenue collapse when only one agent is informed. And then for the two bidders binary signal case, we were able to come up with a unique prediction, and I think that's the first step, of course, in trying to analyze the general case when you have many agents and each one of them have many signals. And we made some progress on that. We're able to, under some condition, to present a strong Tremble robust equilibrium, but we don't have a general result. And I've briefly talked about the mechanism design aspects of this problem. Okay, so thank you.
So questions? Ever?
Your existence is that limited to two bidders only, or is it general for n bidders?
No, actually, the existence, we actually construct the equilibrium, with... Sorry? Two bidders, and for every parameters we prove whether it's a one atom equilibrium or two atom equilibrium. So we don't know to prove that in general. We have like specific constructions for the two bidders, two agents. Okay, thanks.
Okay, thank you.